Hello.
Live.
Hello.
Are we live?
Hello, everyone. This is the Google Hangout for the Global Freshman Academy course, AST111x, Introduction to Solar Systems Astronomy. We have myself here, we've got Caleb, we've got Jackie, and we've got Rebecca. And we'll be doing a little bit of talking about things we do, and then we'll start answering some of the questions that were posted on the discussion board and any questions that you may want to post on the Q&A button that you have access to. You may also send any comments or subject material or questions to the Twitter feed, which has got a pound AST111x hashtag, and you're welcome to do it that way as well. So we'll start off by doing a little bit of introduction on who we are, what we do in this course, what we do a little bit outside this course, and then we'll start taking some of the questions. So Jackie, why don't you start?
Hi. My name is Jackie Munkevich, and I realize that it's a difficult name to spell or pronounce in any language, unless you're actually Polish. The name is originally Polish, but I don't actually speak any Polish because my family has been in the United States for 3 generations. So I'm unfortunately only an English speaker. I'm a teaching assistant in Astronomy 111x. I'm a graduate student at the Arizona State University School of Earth and Space Exploration. I'm an astrophysics PhD candidate, which means I'm attempting to get my doctoral degree in astrophysics. I'm specifically studying cosmology, and we've had a lot of cosmology questions in the course discussion board, despite the fact that this is a solar system based course. But I do actually study it for my research interests. I'm an observer. I work in the low frequency cosmology lab, which actually is at ASU, is run by Professor Judd Bowman. He's my research advisor, and he actually builds radio telescope instrumentation at long wavelengths. So unlike visible light, where the wavelength is like a fraction of the size of your hair, a radio wavelength can be the size of like a Coke can, or it can even be meters. I don't have enough screen to show you how big a radio wavelength is. So long word of the FM radio band typically is where we're looking. And we're looking for the signals of hydrogen immediately after the Big Bang, when the first stars are forming. We're looking for the imprint of the first stars and galaxies forming after the Big Bang. And I'm using a combination of radio techniques and visible light techniques with the sort of telescopes you think of, in addition to radio telescopes, to look for that signal and study the very first galaxies that formed. And I think I'm going to move on now. Thanks. Caleb, it's your turn.
All right. Hi, I'm Caleb. I'm an astronomer at ASU as well. I'm a teaching assistant for this Astronomy 111 course, part of the ASU's Global Freshman Academy. And I'm also a 6th-year astronomy PhD student. Me and Jackie came in at the same year in the same program.
We got to get out of here.
And my advisor is Professor Chris Grappi. So together, Chris and I designed cameras to take pictures of gas within giant molecular clouds. These are regions of cold gas and dust. They don't emit very much light, and they're pretty dark in the optical. They actually block light. So a better question for an astronomer than what's your sign is what's your frequency. So my frequency is a region of the electromagnetic spectrum called the terahertz. And terahertz light is a frequency that's 1,000 times greater than greater than the light that car radio receivers get. So the 100 megahertz light in car radio receivers is 100 times less frequent than the light that I study. So this means that the electronics in my camera have to respond 1,000 times faster using the same techniques. So on the other side of this, terahertz radiation is actually 1,000 times lower in frequency than optical light, or light that you see with your eyes. So this makes the optical techniques difficult to use as well, because lower frequency means less power.
But I'm looking at the optical light, and I'm looking at the long radio wavelength, which is the megahertz. So terahertz, megahertz. So you're in between my wavelengths. You're a million times shorter than long wavelengths.
Right. So I'm at the confluence of the optical and radio techniques, and I like to think of it as the Wild West of the electromagnetism. So in building a terahertz camera, I've learned about electrical engineering, mechanical design, cryogenics engineering, which is mostly that nothing works when it's really cold, superconductivity, control systems, microassembly, and a fair bit of data reduction and math, which I like to do in Python. So one piece of knowledge that I'd like to give to the class, based on my research, is that every measurement has an error, and if you know that error, you can know how useful your measurement's going to be. So hopefully we all find that our errors are small today. And with that, I'll hand it over to Becky. Thanks.
Becky appears to have disappeared.
Oh no.
Okay, looks like we
Oh, there she is again.
lost Becky. There you go, Becky.
Okay.
Okay. Sorry about that. You guys aren't the only ones who have computer problems. So I am also a graduate student at Arizona State University. I've only been here for 3 years. I'm just starting my 4th year. And I am also a candidate to get my PhD in astrophysics. I also am like Caleb. I work with instrumentation, basically stuff that helps us look at stuff in the sky. But instead of developing the cameras that we're using, we are trying to use cameras that have already been made. Specifically, this is a near-infrared camera that was made by the military. The idea being that cameras and telescopes that are already made commercially in some form are usually a lot cheaper than specially designed instruments, but not meant for what we're trying to get them to do, so they might not be as sensitive. But we're hoping that technology now is sensitive enough, is good enough, that we can do real astronomy using a pre-made camera and a telescope that you can buy on the market. And so right now, we are trying to get this camera and telescope to work together to follow stars really, really closely. And we're doing this because we want to be able to observe extrasolar planet transits. An extrasolar planet is something we're going to talk about later in the course, but it is a planet that is going around another star. So a transit is pretty simple. Basically, when the planet is going around the star, it will eventually, in its orbit, cross in front of the star. While it's in front of the star, it's going to block just a little bit of light, and the star is going to get dimmer. And we can tell, because we're watching the star, we notice it get a little dimmer, and we can learn about the planet that's going in front of it. We can learn about how big it is, and about its mass, just based on what we can see about the star. And we're doing this in the near-infrared because a lot of the stars in our galaxy, the most common stars, are actually more reddish. So they're brighter in the red and near-infrared than they are like in the middle of the visible spectrum, which is what cameras normally can see in the visible spectrum. So I'm working, and I'm doing this work with Nathaniel Butler. He's a professor here at ASU as well. That's pretty much my research.
Awesome.
Okay, cool. So my name is Frank Timmies. I'm the instructor of the course. I'm a professor at the School of Earth and Space Exploration, and I'm very happy to be part of the Global Freshman Academy as we move this program forward. Let's see. So the plan of action, we've all kind of introduced ourselves and what we do. Oh, I should say a little bit about what I do. So I'm a theorist. So I make it up as I go along. So I do astrophysics. My specialty basically is stars that go boom. So I study things like supernovae, which come in a couple different varieties. I do things like X-ray bursts, gamma ray bursts, classical novae, basically anything that goes pop has generally got my attention. And then once they go pop, they spit out some elements that make the periodic table, and then how those elements get out into the galaxy, get out to the cosmos, how they get mixed up, and how eventually some part of them make their way into planetary systems to form planets, to form you and me, and we go from there. So that's a little bit about what I do. So the forum, well, I guess we'll do kind of a round table. We've selected a couple of themes that came out of the posts on the Google discussion board. So each of us are going to take a few minutes and cover some of those themes. And once we've sort of done a round robin on that, we'll open it up and kind of take questions as they're coming over the Q&A. We'll cover those along with some of the other ones that were posted on the discussion board. So Caleb, you want to start off?
Yeah, I can start off. So I'm going to talk to everybody about tides today, and for that I'll need a totally different pair of glasses. All right, let's get started.
That is awesome glasses.
Oh, thank you. All right, everybody see my screen? Looks good?
Yep.
So I'm going to start my presentation. It's on tides. And let's just remind ourselves a little bit about gravity. We've been talking about Kepler's laws in this course so far. So gravity decreases as the square of the distance to a mass increases. So the farther away you get, the less gravity you feel. And astronomers like to refer to this relationship as a 1 over r squared force. And so you can see in this part where I put it as a radius of 1, so we're 1 green unit away from the source of gravity, or a big mass. And I've got a normalized gravity here, it's 1. And as I go a little bit farther out, I go twice as far, so a radius of 2 now, my gravity is decreased by 1 to a quarter of what it is before. So here's the square of 2 is 4. So that's the 1 over r squared part of this. And you can continue this trick, and with an r of 3, gravity is a ninth, and it quickly diminishes as you get farther away from the mass. So when we've been talking about orbits, we've been using a convenient simplification. And that's what physics and astronomy is all about, is making simplifications to make everything, make really difficult problems more manageable. So the simplification that we've been making is that all the mass of an orbiting body is in a single point. I call that a point mass. So here's my point mass, and you might imagine it as a planet orbiting a star. That's a lot like the systems we've been seeing. But real masses aren't like this. They're extended masses. So it has both volume and so the gravitational field on one side of that extended mass is going to be bigger than on the other side just by being closer. So there's going to be this gravity difference across the extended mass. And so when we want to talk about the tides and what's going on with them, we have to consider an extended mass, not just a point mass. So I see I've made a little toy, and the radius is 1 on this side, radius is 1.01, and there's a slight gravity difference across that extended body. So what happens to a perfect sphere in this situation? It actually gets a little bit stretched from the gravitational field, and I'm going to go over that in the next couple of slides, how that stretching happens. So here on this side, you see an extended mass, and it's got self-gravity only, and it's a perfect sphere. Excuse me. So it's in hydrostatic equilibrium. Everything has gone to the lowest point that it can. It's in a stable shape. Can't get any more compact. And it's a sphere. But an extended mass is acted on by gravity of a larger mass. And so I've shown some vectors here, or just arrows. Shown some arrows here for the gravity of the big mass. So here, this arrow is longer and darker, so there's more gravity on this side of the extended yellow body and less gravity on this side. And in the middle here, this is sort of the average gravity for the entire system, but it's also the gravity felt at the middle. So what we're really interested in, right, is the difference between a point mass and the extended mass. So the point mass would have a gravity vector that's just like this one, or gravity arrow that's just like this one in the center here. And so if we subtract the average arrow from all the others, this arrow goes to 0 because it's subtracted by itself. This arrow here gets turned into a smaller arrow that points this way. And since this one is smaller than the average, its arrow actually gets flipped around. And these, since they point down a little bit, the difference between those and this arrow makes them point in. So it's this difference that causes the effects of tides. So you can see that there's a little bit of pull just from the mass being an extended mass, a little bit of pull in the axis along which the big mass is gravitating. So if we add the self-gravity and the small gravity difference from being in a non-uniform field, from having more gravity on one side, less on the other, then what we have is less gravity along the axis of the mass and more gravity perpendicular to that. And so what this does is it makes a new equilibrium. So a perfect sphere is no longer the balancing point for all these forces. So it stretches and conforms to the forces that it feels. So this is what gives rise to tides. So on the Earth, the Moon is much closer to the Earth than the Sun. And since gravity is a 1/r² force, the Moon has the biggest gravitational difference across the Earth. So from this side to this side, because the Moon is closer, the 1/r² is more important for creating a difference. And so with the Moon is also changed by its gravitational interaction with the Earth, and the Earth is changed by its gravitational interaction with the Moon. So the Earth's surface is covered with a liquid, and that liquid water, it can respond to the Moon's gravity. But the rocky parts inside the Earth, they're more rigid, and those bonds tend to hold up when feeling these slight gravitational changes. So there's a little bit of squeezing and stretching and friction, but for the most part, they stay in place. But the water moves. So this moving water that's conforming to the gravity from the Moon, that's what's causing the tides. So you can see high tide along this axis that's aligned with the Moon, and low tides are on this other axis, perpendicular to that. So if you see the Moon overhead or at your nadir, directly below your feet, you couldn't see it, but you could know that it's there because you'll have high tide. And if you see the Moon on the horizon, then it's perpendicular to you, and you're at low tide. So as the Moon goes around the Earth, it changes where the high tide is. So the Moon's orbital period is the same as its rotational period. And we have a special name for this we call synchronous rotation. And this is why we only ever see the one side of the Moon. This side of the Moon is always facing the Earth. And we don't know what the craters, or we're not familiar with. We know what they look like. We've been there and sent rockets. And all the craters on this side have unpronounceable Russian names. And this is the side of the Moon with all the valleys and features that we're used to. So synchronous rotation is actually reinforced by these tidal forces. And so if the Moon were to get if its Moon's orbit and rotation were slightly different, the tidal forces act on the Moon and bring it back to synchronous rotation. So synchronous rotation is actually the equilibrium. So that's the end of my presentation. And I think I'll be turning it back over to my esteemed colleagues.
Okay. Let's see. Why don't I take one? Let's see. One of the questions that is coming up in the Q&A part and was also posted a couple of times in the discussion board was sort of about the difference between astronomy and astrophysics and what sort of careers and jobs might be available, what sort of, if you want to continue your study in astronomy or astrophysics, what might your next steps be beyond this Global Freshman Academy course. So historically, astronomy meant observation, and astrophysics meant the application of physics to that astronomy. I would say today those lines are largely blurred because astronomers do more than just record something. They interpret what they're seeing. They're putting it in a larger context. So really, these days, I would claim that astronomy and astrophysics is really kind of one and the same. It's where a little bit you might put a little bit of weight if you're at a telescope or if you're doing theoretical models. There might be a little difference there, but I would say from a practical point of view, they're very similar these days.
Right. If I sit next to somebody on the plane and I don't want to talk to them, then I tell them I'm an astrophysicist.
Right, dude. How many glasses do you have? Okay. So people asked about things like they can do, citizen science, things that how amateurs can make a contribution to astronomy. And there's a number of ways that you can do that. People with telescopes, amateurs often are the ones who will discover supernovae, for example, before the professionals do. They'll also discover a lot of the asteroids and comets coming in, and hence they get to name them as they come in. Because by and large, the professionals are going to be using big telescopes that cost a lot of money. They're going to be looking deep. They're looking at fainter stuff that the amateurs can't touch. So where amateurs make a big contribution to astronomy is stuff that is brighter and nearby, where you're not going to put the investment of a big telescope looking for that. The advantage of amateurs, too, is you can sit on an object for hours and hours and hours, if you like, or do a scan across the sky. And so this is why most of the discoveries historically in supernovae or near-Earth objects, NEOs, have been discovered by amateurs. There's other things that you can do if you want to make a contribution to science. You can get involved in a citizen science project. There's a whole number of those. There's stuff over at Hackspace. There's stuff over at Boink. So you can do things like search for aliens. We'll cover that a little bit toward the end of this course. You can help the search for extraterrestrial intelligence by downloading a program. And what that does is it takes radio data from primarily Arecibo, but other telescopes as well. And it's at a particular wavelength. It's around, well, it's between 18 centimeters and 21 centimeters. And what you're doing is you're you're looking for the power within those bands, and you're looking for a signal. And so you can help search for extraterrestrials there. There are other ones, such as Zoo Universe, where you can learn how to classify galaxies and help the cataloging of galaxies, the various types that go around. So there's a whole number of different types of citizen science where you can get involved in discovering exoplanets, discovering pulsars, discovering black holes, discovering aliens. All this is available to you if you want to do it. So go ahead and take a look at Boink. Go ahead and take a look at some of the citizen science projects that are out there if you want to do that. There's also a number of what are called pro-am collaborations. So this is a collaboration between amateurs and professionals. And if you look at magazines such as Sky and Telescope, they usually have a fair amount of information on available pro-am collaborations that you might consider joining. There are also a number of ways that you can help process images that that come off some of the major telescopes, such as the Chandra X-ray Observatory or the Hubble Space Telescope, or in the relatively near future, the James Webb Space Telescope. And so you can get involved in some of the image crunching there. And if you have a particular bent, there's also things that are crowdsource funded to do particular things associated with various parts of astronomy. A couple of them are known as Fund-A-Geek and other assorted examples. So you can contribute to astronomy that way. Next steps after this course, if you're interested in doing something in astronomy, would be, well, do your homework a little bit, poke around, see what's available, find out what your interests are, because just doing something in astronomy and in astrophysics is an incredibly large topic. And so as you heard from the introductions, everyone sort of narrows down where they become an expert in that particular area. They certainly know a broad swath of astronomy and astrophysics, but you generally have a specialization. So beyond this Global Freshman Academy, I would look at what's available at your local college if you're interested in doing that. Getting your bachelor's in almost any topic is fine. So whether it's physics or computer science, mathematics, chemistry, all of those are good background material for astronomy and astrophysics because there's just not a lot of undergraduate, really strong undergraduate programs in astronomy and astrophysics. So most of us have been accreted on from other more specific topics. Jobs that are available, you don't have to get a PhD. Generally, you're going to be in a research mode if you're getting your PhD. But if you have a background in astronomy and astrophysics, whether that be a bachelor's or whether that be a master's, there are a number of jobs that are available. For example, you could be a support specialist at a government laboratory such as NASA. You can be a research assistant at some of the national observatories. You can have public program specialists at various science museums. You can be an education specialist at planetariums. You can be a programmer for various computer applications or analysts. You can move that into a teaching if you would like to teach K through 12. If your bent is more toward writing, there are certainly positions available at, for example, astronomy magazines, various blog sites. You can freelance if you would like to do that. There's also a chance to influence the local political or the national political scene. There are definitely intern positions available in Washington usually, associated with a Congress or Senate, and so you help digest the material and float recommendations up the line to your congressman that you're working for or your senator. There's also data analysts, right? Big data is a thing these days, and there's lots of positions in the aerospace industry for data analysis, for visualization, these kind of topics. And of course, there's always the graduate student route. There's the academic route. Where you're primarily going to be focused on research on a particular area. So that's a little bit about sort of next steps that you might take in this course. If you're just interested in astronomy, you just want to help out in the science, you want to just help in that regard, or if you'd like to move it on into something you might consider as a job or a career possibility. And with that, I think I will turn it over to Jackie to cover some of the topics.
Okay, I saw a number of questions about constellations on the discussion board. and I'll answer some of the Q&As as well. But constellations generally, we did cover some constellation stuff, some basic orientation of the night sky stuff. In the material of the course, we told you about the North Pole star. The celestial North Pole has a star associated with it called Polaris. There's also a celestial South Pole. And these are the areas of the
Okay, we seem to have a technical glitch there. Okay, Jackie, you're back. You dropped out a little bit there, internet connection.
Sorry. The celestial North Pole and the celestial South Pole are the only two places on the globe in the sky, on the celestial sphere, that we can say are directly over a part of the globe, because the Earth is spinning, and because the Earth is spinning, no other part of the sky is ever directly over the Earth for long. The rest of the sky appears to spin around us, but in fact we're the ones spinning. So the celestial sphere does not move. We are the ones moving. But at the North Pole and the South Pole, the axes of the Earth are fixed. That's what we're spinning around. And so those two parts of the sky, they're the most important two parts of the sky in whatever hemisphere you're in. And being able to locate them is the most important thing. So being able to find the North Pole and the South Pole. We've told you a little bit about that. We've also told you about the zodiac, which is the constellations. Those are the 13 constellations that the sun and planets travel through. And those are aligned with the ecliptic plane of our solar system. And there's been some questions as well about why do we have an ecliptic plane? Why are all of the orbits of the planets lined up like that? And that's an interesting question and a very deep question that we're going to get into later in the course. And it has to do with the formation mechanism of the solar system, but that's a bit of a spoiler. And then for the rest of the night sky, people want to learn constellations. That raises the question of which constellations do you want to learn? We've introduced the Greek and Arabic system, the Mediterranean system, and I'm going to emphasize it is a Greek and Arabic system. The Greeks weren't the only ones to split astronomy and astrology. Most cultures, astronomy and astrology, if you want to study astronomy, you are essentially studying astrology. You're looking at both the myths and whatever science that culture had. They tended to be intertwined, and the Greeks were the first to start tentatively splitting these two fields via the scientific methods. But we don't give enough credit to the Arab cultures that were at their height during the Dark Ages of Europe. The Arab cultures also made this split more permanent. And so when you look at the night sky, according to European Western constellations, you'll see constellations that they have Greek names, planets have Roman names, but the stars themselves have Arabic names. And so you'll see a lot of stars like Elbirio, Aldebaran. They all start with Al, Al this, Al that. And that's because they're intrinsically Arabic named stars. And it's because this culture of sharing these constellations happened in the Mediterranean and was between these cultures that were along the Mediterranean Sea. So the Greeks, the Romans, and all of the Middle East were sharing this navigational skill set that developed the constellations. There are, of course, and every other culture has a set of constellations and stories to go with it. So I'll talk briefly about the Western constellations, the Mediterranean constellations, very briefly, for those of you who are interested. But the best way to do it is to either find a planetarium or, better yet, go out to the night sky, find your north or south celestial pole. And I actually posted on the thread how to find the south celestial pole. It doesn't have a handy star, so it's not the easiest one to find. But you can use the Southern Cross to find it. And get one of these super handy night sky guides. Make sure that it's correct for your latitude. So it'll say the night, whatever, this star wheel. They're called a star wheel. It'll tell you what latitude it's correct for. And this is mirrored, I think, in the image, which is annoying. But this one says 30 degrees to 40 degrees north latitude. So this is correct for Phoenix. If you go more farther north, you'd want a 40 to 50. If you go farther south, you want an equatorial one. Obviously, if you're in the southern hemisphere, you'll want to acquire a book like this. the Australian sky or Southern Hemisphere sky, because this information is not terribly useful to you. And then what you really need to do is just sit there and find stars. And you can match the correct date and the correct time of night. So the wheels are great because they move the same way the sky does. And so you can find today's date, September 1, and you can match it with your time that you're going to do your observing. Let's say we're going to observe at 8 p.m. right after sunset. So you match your date, September 1 to 8 p.m. and ta-da, this is the sky as you would see it. And we have north over here. This is the north celestial pole that everything is spinning around. That's Polaris, is right under that pin. And then the zenith, the point directly overhead, the zenith, is in the middle here. It's not the point, it's this point right here. And so north, south, and they're all meant to be held overhead so that you can orient to the sky. These things are all flipped backwards. If you try to orient holding it flat, if you try to orient north, south, east, west, you'll get north and south correct, and then east and west will be flipped, because they're all meant to be held over your head. This is the best way to learn the night sky, is to get a star wheel. I also brought an Autobahn guide. This is best for the northern hemisphere because it has lovely star charts. And we actually use these in the in-person labs in Astronomy 111 on the Arizona State campus. And we don't necessarily teach the constellations, we teach you how to learn the constellations on your own. And this book is actually what we require. So the Audubon Guide, it's perfect for the Northern Hemisphere. If you're going to look at the Southern Hemisphere, it's still great because it has all the information, the beautiful pictures of all the nebulae and star clusters. It's got information about each of these astronomical objects. It's beautiful. It's got each constellation is mapped out. But when you get to the October sky, the thing you want, what am I looking at right now, the October sky? It's northern centered. So at that point, you want to find yourself a little Southern Hemisphere book if you're in the Southern Hemisphere, so that you can see what you're looking at in the Southern Hemisphere. So that's your basic orientation of the constellations. I'm going to do a quick screen share so you can see what's up tonight. Screen share. Okay. Tour the September sky. Screen share. Give me a sec. Sorry, guys. Google Hangout. Screen share. Okay. Desktop. All right, and so I am looking at a picture of. Hey, do you guys see this?
Yep, sure do.
Okay, awesome. All right, so here in the fall sky, one of the first things that I want to draw your attention to is the bright star Vega, which is still kind of almost directly overhead, right at sunset, in the northern hemisphere at my latitude. So if you're in the northern hemisphere, the thing that you're going to be looking at is, right at sunset, is the summer sky. So at the beginning of the night, you're looking at the summer sky, and then it drifts over to the autumn sky at midnight. And so when you look, so I'm looking north in the northern hemisphere, and viewing, so here's north in the northern hemisphere, here's south in the northern hemisphere. So if you're looking south, but more or less straight overhead, there's this thing called the summer triangle. And so this is what you would have seen directly overhead at midnight in the middle of summer, and you can still catch it at the beginning of the fall. And so these three stars, Lyra, Cygnus, and Aquila, this is the very first thing you should orient to if you go out in the night sky at night. And then if you're at a reasonably dark place, you're not in the middle of a city, you might be able to see the Great Square rising in the eastern sky, and that's the signature constellation of the southern sky, of the autumn sky. In the north, the autumn sky is a bit boring because we're looking away from the Milky Way. So if you see this fuzz, the fuzz on my map, that's the Milky Way galaxy, and so you'll often see the fuzz going through the map, and the fuzz represents the Milky Way galaxy. And in the autumn and the spring, we're looking away from the Milky Way galaxy. Our night sky is faced away from the Milky Way galaxy. And I'm going to ask people, but I'm not going to answer it. You can put it in the Q&A if you think of it. Why do we see different constellations at different times of the year? Why, when we look out at night, at midnight, do we see different constellations in the winter sky versus the autumn sky versus the summer sky? Why do they look so different? The autumn sky and the spring sky tend to have less bright stars, and that's because we're looking directly up and out of, or down and out of the Milky Way galaxy. The Milky Way is kind of a disk, a frisbee. We are fundamentally looking away from it, out into the depths of intergalactic space. In the winter and the summer, we're looking through the Milky Way, where all the nearby stars are, and so we see bright stars like Vega and Deneb and Altair, which are very bright, and they're in the Milky Way and they're nearby, and they're more interesting. In the northern sky, of course, we'll have the North Star, which is anchoring our sky, and you can use the Big Dipper. The cup of the Big Dipper, the bowl of the Big Dipper, has these two pointer stars you can use to orient to the North Star. But if you can't find the Big Dipper down the horizon, you can use the constellation Cassiopeia, which is this little, right now it looks like an M this time of year. Other times of year it looks like a W. These are circumpolar constellations that go around the North Star. They never quite set. They just skim along the northern horizon. And Cassiopeia will look like a W when it's below the North Star. But when it's an M, you can sort of use the dip of the M to find the North Star, which is attached to the Little Dipper. So that's a basic orientation. And I encourage you guys to go try to find the stars yourself, get yourselves a star wheel, and go for it. And I think that's what I have to say on constellations today, Frank. So basically, okay, I'm going to move on.
Thank you, Jackie. That was great. Becky.
I should unmute myself. That'll help. So I've been just sort of glancing at the questions that people have been putting up, and there's been a lot of questions about the moon in general. One was a misconception. The moon is moving away from us at a centimeter a year. It's not moving towards us. It's moving away. And then I've seen a few about just like the color and size of the moon. For the most part, when you see an orange moon, it's just the fact that the moon is close to the horizon. And so the moon, when you see the moon, all you're seeing is the light reflected from the sun. So when the moon is close to the horizon and the sun is actually shining through the atmosphere, you're just seeing the light coming. I think I got that backwards. Basically, it's because the light's coming through the atmosphere. And I think somebody asked about blood moon, and I think that is what they're talking about. So the blood moon is got more to do with lunar eclipses and how far apart they're spaced. And I feel like I went through that a lot faster than I meant to. What was the other thing I was going to say? I don't remember. So I was also going to go back to one of the original questions that was back in the suggested topics, which was how to get people interested in astronomy. That's something I've been involved with a lot. ASU has a huge outreach program where we give these big open houses and invite the public to come in, and we come up with a lot of different activities for kids to do. And for the most part, what I've learned is that you definitely, if you want to bring kids in, you can show them what's up in the night sky, but what seems to hold them is whether they can do something in front of themselves. We have done stuff where we've made different types of balloons and shown what would happen to them as their life moved onward, showing like the different sizes and how if something goes supernova, the stuff inside of it's going to spread everywhere, or building paper models of satellites and stuff. It's giving them something to do, and then if you can get them out to telescopes. There are a lot of places in the U.S. where there's like astronomy clubs that will have get-togethers, and you can take kids out and they can look through telescopes, and that's really cool for kids. So it's mostly just having them have something in front of them they can actually do. Make them realize that science is something cool that they can actually participate in. And that's basically my experience, and trying to get them out and about as much as possible. That was
Hey,
Jackie?
Becky, I see a question about how do we, it's got +10 on it, so people like this question. How do we know the mass of the sun?
Oh, I scrolled down. I didn't see that one. The specific mass, as in when we use Kepler's laws, that's there's been a few questions in the discussion board about how the Kepler's laws work, and they're based directly on the sun. They're based on, I'm going around in circles on this one. We know using Newton's laws about how heavy the two masses are relates to how quickly they go around the sun, and I can't remember specifically how we determined the mass of the planets to get the sun.
We need to get that gravitational constant, that big G. When you write out Newton's law of gravitation, it's got this gravitational constant G in there, and so the whole mass of the sun, we can get it relatively, but until we actually know what that number that we throw away every time we talk about it in lectures, the constant is the thing that actually anchors it in kilograms or pounds. We actually need that constant. And when I was an undergraduate physics major, some of my compatriots in the physics lab chose for one of their senior physics lab experiments to measure the gravitational constant. And they measured the gravitational constant in the laboratory space. And no one was allowed in the room. It's such a delicate measurement to make. When you're not talking about planets, when you're talking about people have a gravitational attraction to each other.
Right, any two masses will have some gravitational attraction.
But it's dominated. Every interaction we have in the daily world, we completely ignore our gravitational attractions to the bamboo behind me has a gravitational attraction. We completely ignore this because everything we do in our daily life is dominated by the huge mass of matter that's below us, which is the Earth. So all gravity that we ever think of in terms of gravity is this big thing that we're standing on, which is the Earth. But we do actually, there is a very slight gravitational constant, or a very slight gravitational attraction between these two books. And I can measure that. And I know how much they weigh how much they weigh on the Earth because of the Earth's gravitational attraction. And then I can measure their attraction to each other. And it's so slight. It's like a millionth, a billionth of a little tiny attraction compared to the gravity here. So it's really annoying to measure. And so these two students would not let anyone in this room for about a month because they had to measure this slight attraction. And if a human being walked into the room, they would throw the whole experiment off because they had gravity too. And it's such a slight thing. And so like the fact that there was construction going on 2 doors down was messing up their experiment. Over the years, they've managed, different laboratory groups have managed to come fairly close to the gravitational constant, but it's really hard to measure on Earth. But we have done it in much more controlled circumstances than a undergraduate physics laboratory can do it. We have done it, and once you have that, then you can plug it all into Newton's laws and actually say, okay, this is the mass of the Earth and the Sun.
Yeah, after you have the gravitational constant, then it's the application of F equals ma, and just replacing things for the acceleration. And then chaining that from knowing the acceleration of the Earth and how much gravity it has, and therefore how much mass it has, to how much gravity we're getting from the Sun. And gravity is always proportional to mass. Gravity is how mass communicates with other mass.
Okay, great. I'll take one of the questions. So one of them questions is, what is the what is the moon made of? Or rather, what is the composition of the moon? And we have some humorous responses that it's made out of blue cheese. That's probably not quite right. But one of the topics we will cover later in this course is the birth of the moon. But we can say a little bit about it right now. There's essentially 3 classes of ideas of where the moon came from. So on the one hand, you could say that the Earth and the moon were born together. So that's the sister theory. And because the moon and the Earth are made out of the same, came out of the same material that formed the other planets, the moon is basically made out of silicates, out of rocks, and some metals. In all cases, all the scenarios, that's the case. The moon is made out of silicates and metals. And we know this because we've landed on the moon, and we've brought back samples, and we can do all the testing. But just a little bit. So we have the sister theory that the moon and the Earth were formed together. We have the interloper theory, which is that the moon was captured by the Earth and put into a gravitational orbit. We do see examples of capture out in the outer solar system. And then you have the mother-daughter theory, where the moon was born from the Earth as a result of a titanic giant collision. And I would say that the preponderance of the evidence these days points toward the mother-daughter theory, that the moon is actually part of the Earth, and we will cover reasons why that evidence points us toward that direction. But at the end of the day, to answer your question, the moon is made out of rocks and metals, just like the Earth is. Let's see.
Well, more specifically, it's made out of basically the same rocks, metals the Earth is made out of because they came from the same thing. Mm-hmm. Is that a spoiler?
Nope, not at all. That's the mother-daughter theory, right? If Earth is the mother, and then the daughter is going to be pretty much made out of the same stuff. So the moon is us. Let's see, another one. Let's do one that's got a +4 here. This will be for our what makes space so cold? Who wants to take that one?
I can take it. So space is cold because there's nothing heating it. So the first law of thermodynamics is that heat only moves from a hotter body to a cooler body. And that seems pretty obvious when you first say it, but if you think about it a little longer, I think it's actually kind of deep. So you have to have something that's hot to move energy to something that's cold. So on the Earth, we're getting our heat from the sun, and we're getting heat from radioactive decay of heavy metals within the Earth's interior. So that's the reason the caves are always at a constant temperature, because they're getting heated from the center of the Earth. In addition to that, we've got this great atmosphere that we can even see through. Oh, I'm getting lawn care outside. So we have this great atmosphere we can see through, and it also wraps us up like a blanket. It keeps us warm at night, and it keeps some of that heat that we get from the sun during the day and helps us keep it in. The lower, closer to sea level you live, the more of a blanket you have. So in space, you don't have that blanket. You only have radiation from the sun. So that's your only source of heat is starlight. The farther away you get from the sun, the less heat you have. And whatever temperature you're at, if you're colder than your surroundings, and your surroundings might be absolutely nothing, you're going to continue to lose heat through light until you're exactly the same temperature as what your surroundings are. That's why Pluto's so cold. It's so far away from the sun. It's barely getting any heat from it. And any internal heat gets radiated away.
I think, I mean, the question is, it seems very sensible to ask what makes space cold, but I think the real question is why cold is the default setting for our universe at the moment. And a more interesting question is actually, why aren't we cold, which is what Caleb has basically told you, which is because we're close to the sun. Space was originally, after the Big Bang, space was as hot as the surface of the sun, or hotter even in the few seconds after the Big Bang. And as the universe expanded, there's only so much energy in the universe to begin with, and energy is heat. I know we said we weren't going to do new cosmology. We kind of have to do this to answer why space is cold. When you stretch the universe out, you take the same amount of energy and you spread it out First you spread it out over twice as much volume, then over 4 times as much volume, then over nowadays we're over millions or billions of as much. We have millions or billions much more space in our space. That makes sense. We have the same amount of energy we started with. So all of the observable universe, everything that we can see, all 13 billion light years of it in every direction, used to be compressed into the size of a basketball at one point. And so that was, all of that energy and matter was very hot. And then it expanded to something the size of the Earth, then to something the size of the solar system. And so all of that, as it expanded, the same amount of energy got spread out. And so there isn't very much of it. So the temperature of space right now is 3 degrees Kelvin, which is 3 degrees above absolute zero. Or negative, what is that, negative 270 degrees Kelvin, or negative 270 degrees Celsius, is that what that is? So we're really cold out there. But it used to be the temperature of the surface of the sun, because all of that energy was squashed together into a much tinier space. So space is cold because it's expanding, basically.
Great. Caleb, this one will be aimed at you a little bit, since it's related to what you talked about on tides. This one's got 4 votes. If the Earth, or excuse me, let me read the question. If the Moon is moving closer to the Earth, why is it moving away from the Earth a centimeter a year? So Becky took part of that. So based on tides, can you say a little bit about why the Moon is moving away from the Earth?
Right. Because of the way that tidal forces are deforming the Earth's surface, they're changing the way the liquid water flows over it, and they're actually stretching and straining the mantle a little bit as well. And so that's creating heat, and that's dissipating energy. And so nothing's free. Nothing's free in this universe, and so anytime you have energy dissipated, it has to come from somewhere. And where that's coming from is the angular momentum of the system. So the Moon is losing a little bit of angular momentum and exchanging angular momentum with the Earth.
Great. Big data is very popular today. Do you have some methods from big data for your astronomy tasks? I can take that one a little bit. Yeah, well, big data is popular because nobody wants to do little data. So big data comes in a variety of forms. It can come in volume, just because you've got petabytes, or you've got terabytes, or exabytes of data, so you can just have a whopping amount. Those can come from observational surveys. Those can come from calculations that you would run on supercomputers. But big data can also come with velocity. It may not be a lot in any one chunk, but it's coming at you at a tremendous rate. And so you've got sort of getting overrun by ants on the big data issue. And there are some other aspects of big data is the way that it can come at you. So depending on whether how it's coming out, you've got different types of tools that you will do to filter the data, to visualize the data. I would claim that a lot of that science is a little bit incomplete at this point. I think everyone is sort of struggling a little bit to how to deal with the data. How to extract what you want out of that data is actionable knowledge. And I would say that whole field of how you extract actionable knowledge out of a big data set is kind of where we're at the bleeding edge of data science. Anybody want to add anything to that one?
That's actually one of the big things that my professor does is he has a camera on, my advisor, Nat Butler, has a camera down in Mexico, and they bring in a lot of data, and he had to actually format a programming pipeline system to get the data down off the mountain and process it as much as possible so that we can work through the data without spending, weeks just running it through the program. So it's a huge thing of how to make the whole process more efficient so that we can do something with the data.
Yeah, I think it's a trend in astronomy that we're exchanging human mind power for CPU time and just checking lots of stuff.
Well, that's
we're always
okay.
getting more and more data, more cameras, and we try to do things in an automated way and move it into the future.
Astronomy data is incredibly data intensive. I mean, like these days, personal computers tend to outpace the needs of the individual human. Most people just use it for surfing the web, word processing, but astronomers.
Okay, Jackie, you faded
Image
out.
cubes.
Okay.
And they're just huge quantities of data. You know how much relative space the images you take with your camera take up on your computer. Well, that's what we do for a living. It's just huge. Big data is big in astronomy.
Right. We're trying to squeeze everything we can out of it too. Just use the math to get every last bit of data out the bottom of the pot.
We call data processing reduction. You reduced all of these images that you took with the Hubble Space Telescope into like one scientific result. But it's hilarious that we call it reduction because as a graduate student experiencing the process of data processing, data quote-unquote reduction, what I end up with is I start with 100 gigabytes of data, and 3 weeks later I have 4 terabytes of data. And I don't know where to put it, and I'm afraid to delete it because there's like important steps in there that maybe I'll regret it. Frank, can we talk about there was a question about the math and the math requirements for the course and the formula, and if there's any assistance we can provide for people who are struggling with it.
Sure, and I think we'll end this Google Hangout on that note, so we'll cover that one. We've been on for just a shade over an hour, so we'll take that last one. And in advance, I'll say apologies for not getting to everyone's question because there are a lot of them. But give us some feedback on what you thought about this Google Hangout. It's an experiment, so give us some feedback on the discussion or on the page how that went. We're currently scheduled to do one more, but we could potentially do others if people found this useful. So let us know what you think about that. And with that,
I kind of liked it.
Yeah, it's kind of fun. It's office hours for 15,000. So yeah, let's go ahead and talk a little bit about the math in the course. Why don't you go ahead and you want to lead off with that, Jackie? Okay. Becky?
I muted myself. Becky, take it.
It was mostly just about whether we're going to go through. I can't find the question. I read it way back.
Yeah, the question is sort of the level of the math and is help available. At what level is that help available, and so on?
If you are having difficulties with the math, always post it. Don't put down the exact numbers that you're getting, because we want you guys to all work this stuff out yourself. But we are always here to help if you have problems with the math. I don't think have any math that doesn't show up on the math handout. Or is explained in the videos. And I can't. Is there more do you want to add?
So, so we're not currently doing previous in other courses. We've done teaching assistant tutorials, but there's not enough time, and we have to go through so much material this first run that teaching assistants don't have time to do little tutorials. In the on-person classes, I'll send them to math tutoring. I'm wondering if there's YouTube help. I'm wondering if you're struggling with fractions, or you're struggling specifically with powers of 10, or the whole cube root, square root thing. If you're having a hard time with a specific math issue like fractions or exponents, if there's YouTube help. There's YouTube help on how to change a bike tire, so there's got to be YouTube help on fractions.
Right.
I mean, I've
We're
seen
willing
YouTube
to
help
help
on
you
quantum
find that.
mechanics. There's got to be YouTube help on math. Like, they've got every math areas that I've noticed so far, so I think they get tutorials on everything.
No,
Yeah,
we're
we'll
willing to
certainly
help with problems and also find you those YouTube videos and
Yeah, that's right.
get
We
you
can
get
search
you
them out
started
for you.
on your journey.
Yeah.
We will do the quality check up front so that you're getting good material as opposed to
That's right.
some random
Yeah.
Google search where something comes up, because who knows what you find on the internet, whether it's good.
So if you have a particular formula and you say, this formula, I am having an impossible time using this formula to get the right answer. Usually that formula, it's either a problem with powers of 10 or exponents or fractions are the usual issues at this point. And so we can go search out the specific video for you. We can't hold your hand the whole way because there's 15,000 of you and we don't have enough, but we can help you find the resources that can help you.
Okay, and with that, I think we'll end this first Global Freshman Academy Google Hangout on air of Astronomy 111x Introduction to Solar Systems. Thank you so much for listening in. We will post a link so you can watch this on YouTube in retrospect, and we look forward to doing another one, and we look forward to interacting with you on the discussion boards. Bye-bye.
Bye, everybody.